Hello friends, we were discussing plastic deformation in the previous lecture. Okay, so let's go forward and discuss plastic deformation a little more. So this one more lecture is devoted to plastic deformation, and in this we will look at that how the stress strain curve you are going to get for single crystal, for example. Okay, and then we will look at the another type of deformation mechanism, that is called twinning. So, if you look at a tensile curve of a single crystal, okay, so initial studies when people were trying to understand this deformation, okay, people did on the single crystal to at least understand that what is the role of crystallography or crystallographic planes, direction in this whole deformation process. So, the Schmidt factor which we discussed, that is also for a single crystal. Okay, that is why you are able to tell that what is the angle between the tensile axis and the crystallographic plane, or what is the angle between crystallographic direction and tensile axis. Okay, in a polycrystal, because every grain will have a different orientation, you cannot say for the whole single sample. So, those work or those analyses are only for a single crystal. So, right now we want to understand that if you take a single crystal, what will be your tensile curve. Already we have seen tensile curves, okay, but those are for all polycrystalline material. So, let us see what happens if you take a single crystal. Okay. So, if you take a single crystal, okay, again we will start with the elastic part, of course, okay, and then you have what we call as a stage 1 deformation, okay, then there is a stage 2 deformation and stage 3 deformation. What do we mean by these stages? Stage 1 is easy glide, means whichever plane has satisfied the maximum Schmidt factor, okay, that will of course take part in the deformation. Okay, so all the deformation is right now taking place on those planes where the Schmidt factor is satisfied, or where you have found the highest one, and the shear stress on those planes in that particular direction has reached the critical resolved shear stress. So, then the deformation will take place. So, this is easy glide, all the plane of that particular orientation are taking part in the slip process. And then you have a linear hardening. Okay, we have not discussed too much detail about this single crystal deformation, because the course is in this particular course we cannot go into that kind of details. But actually when the deformation takes place, there is a rotation in the crystal, and later on we will find that some other planes are also satisfying the condition of maximum Schmidt factor, and there is another planes and direction where the deformation is taking place. Okay, so when this dislocation on two different slip planes start interacting, okay, you have this stage 2 hardening. Okay, that means this is actually related to dislocation interaction. When two or more slip system are active, whereas in this case only one slip system is active. Okay. And of course, later on when you have a kind of saturation, that how much strain a material can take, okay, you will start seeing that there is a decrease in the rate of the hardening, okay, and it is almost becoming a non-linear parabolic kind of curve. Okay, so that is my stage 3 hardening in a single crystal. So, if we want to look little bit in detail, so in stage 1 you have easy glide, okay, and of course there is no strain hardening. You can see that as a function of strain, okay, my stress is constant here, okay, so there is no strain hardening. Single slip system with highest Schmidt factor is active, as I told you just now. Okay, so in this stage 1 only one slip system is active. Then comes the stage 2. Okay, now you see actually the strain hardening part. This we will again come back when we will discuss the strengthening mechanism. that what do we mean by this strain hardening. Why you get strain hardening? Because now multiple systems, slip systems are active. Okay. So, now dislocations are now interacting with each other, and now it is becoming difficult for a material to deform. Okay. So, it is giving a response in form of higher stress required for deformation. Hardening due to dislocation interaction, as I told you that multiple slip system become active after a certain point, okay, and that is actually because I will just tell you that what do we mean by this, actually why this multiple slip system become active, that is because of crystal rotation. Okay. Then we come to the stage third, where you have decreasing strain hardening, as I told you. Okay. So, these are the three stages of deformation you will see in a single crystal. Okay. Now, how it will be different from a polycrystalline material? Okay. So, already we have seen that in a polycrystalline material you again have elastic part and then the strain hardening part. So, this is strain hardening part in polycrystal. Okay, where you have uniform elongation, and then after this is the point where somewhere the naking will start. Okay, and then you have a non-uniform deformation, whereas in single crystal you have a kind of a no strain hardening region, then the linear strain hardening region, and then a non-linear strain hardening region. So, if you compare these two, you have higher yield stress in polycrystal, okay, and higher strain hardening. Okay, as compared to a single crystal, you get more strain hardening in polycrystal, and at the same time the yield point, okay, the yield stress is also higher in case of polycrystalline material. Okay, the reason is that because of grains, okay, there is lot of when you take a single crystal, okay, there is no constraint on the crystal from surrounding. Okay, it is just there is only one constraint on the single crystal, the way you are deforming. So, you have to hold the sample, so only those ends are under constraint, but on the sides there is no constraint. So, now if you understand that I start putting the constraint from the sides, okay, then now it becomes even more difficult for material to deform. Okay, and so both the yield stress will increase and the strain hardening capability of the material will increase in polycrystalline material as opposed to a single crystal. So, if we want to understand this strain hardening part, okay, so what happens? You have a elastic part, okay, this is your yield point, and then you have a plastic deformation, uniform plastic deformation. Okay. So, I am giving strain to the material, as you can see here. Okay. So, this is let us say I can call it as epsilon 1, this I can call it as epsilon 2, okay, and corresponding stresses are there sigma 1 and sigma 2. Okay. So, as a function of strain, okay, if I am keep on putting the strain in the material, my response of the material is becoming higher and higher. That means the resistance to deformation is becoming higher and higher. Okay. So, the response of the material is measured in terms of stress. So, as I am putting strain in the material, the stress, the response of the material is also increasing. Okay. So, that means by imposing strain in the material, I am able to harden the material, I am able to increase the strength of the material, and that is why we call it a strain hardening. Okay, my material is becoming harder to deform. Okay. So, the stress strain curve in the region of uniform plastic deformation exhibit strain hardening or work hardening. So, either you can call it as strain hardening or you can call it as work hardening. Why we call it as work hardening? Because people used to saw that their material is getting hardened if you are working on it. Okay. If you suppose do any work on the material, suppose you are just hammering if you take aluminum for example bar and you start hammering that, okay, you will see that after some time it is becoming difficult to deform or to give the same amount of strain as you were able to do when you just started working on it. Okay. So, that means the material gets work hardened, okay. You are working on it and it is getting hardened. Okay. In more technical term, actually what you are doing is you are putting strain in the material and the material is getting hardened because of this strain in the material. So, you can either call it a strain hardening or work hardening, both the term means same thing. And if I want to express this non-linear behavior, I can express the stress in as a function of strain, okay, with a power over it, okay, because it is some kind of a exponential behavior, okay. So, my stress is dependent on strain and with an exponent n, and k is your some material constant. So, your sigma is true stress, okay. Of course, we will do all the analysis using true stress analysis. Right now what we have drawn is actually engineering stress strain, but we will do all the analysis using the true stress curves, okay. So, it will be like this, something like this, okay. So, we will do all the analysis using true stress and true strain. So, sigma is true stress, epsilon is true strain, k is a strength coefficient equal to true stress at epsilon 1. So, wherever you get 100% strain, whatever is the true stress value will be there, that is my strength coefficient. Your n is the strain hardening exponent, okay. And how I can get that? If this particular equation is exponential. So, basically if I take logarithmic on both sides, this equation will become something like this, okay. So, your exponent will come here when we take log like this. So, it is a now equation of a straight line with a slope n, okay. So, it is y is equal to mx plus c kind of equation. So, where m is your slope, okay, and that is equal to n. So, if I plot this particular equation on log, okay, with sigma versus epsilon, ln of sigma versus epsilon, then n will give you the slope, okay. So, if you see, it will be a simple curve like this, ln epsilon, ln sigma, and it will be some straight line like this. You will get some points for which you will have a best fit line here, okay, and the slope will give you the this strain hardening exponent, okay. So, this is how you get the strain hardening exponent from the experimental data. Now, coming to another type of deformation mechanism, okay, as I told you that one of the deformation mechanism is what we have already discussed is the slip process, okay. So, basically two atomic planes slip over one another, okay. In fact, the closest analogy you can take for this kind of slipping process is if you take a deck of cards, okay, playing cards, you put the deck like this and you just apply a shear stress on the deck, okay. What will happen is you will start getting shear deformation, okay. And microscopically if you see, okay, let me just we are discussing this. So, suppose initially this is how your deck of card will be, okay, and now you are applying a shear stress here, okay. This is this end is at the lower palm, the upper palm is applying the shear stress, okay. So, what will happen, this deck of card will slip, okay, and you will see that it is becoming something like this, isn't it? If macroscopically I see, okay, macroscopically in relative term of course, okay. Microscopically if I want to see for each card, what I will see? I will see that each card has displaced by some amount. So, actually at the level of card you will see that each card is displaced by some amount, okay, and so on. So, each card has displaced by some amount and that is what is creating this total shear. So, you can consider each card as plane, okay, over which you are applying the shear stress, and the planes are getting deformed. So, you have crystallographic planes like this, okay, and they are getting slipped, okay. So, after some time this one will slip, and so this is the first plane, okay, then the next plane is slipped by one atomic distance, for example, another next one is slipped over this one, then third one is slipped over this one, okay. So, though this is at atomic distance in terms of crystal planes, okay. Now, if you see macroscopically, okay, if I do not go into the up to the atomic scale, what I will see, I will just see one plane like this, that initially it was like this, and now it has deformed by an amount like this. So, this is what is the slip process for deformation. So, for plastic deformation, now it will not come back, okay. Once it is slided, it has slided. So, I cannot bring it back to the original position. So, this is my slip process for plastic deformation, okay. Now, coming back to twinning, okay. So, twinning, already we have discussed that the crystal across the twin has the mirror image, okay. So, basically your atomic arrangement across the twin is something like this, then across the twin you will have mirror image of this, okay, atoms placed at the just what you will get a mirror image if I just put a mirror here, okay. So, that is what you have deformation by twinning is mirrored over this one, just to make it more clear with a nice image, okay. So, this is how the twinning is going to be. So, deformation twinning, okay, it is also known as mechanical twinning, because twinning can be by two reasons, okay. One is through deformation process, for that we will call it as mechanical twinning. Sometimes twin forms during the annealing process also. So, those twins are called annealing twins, okay, during the transformation and so on, okay. So, those are annealing twins, and these are because of some mechanical deformation. So, that is why these are called mechanical twins, or you can call this in deformation twinning. Very important mechanism for deformation other than slip. So, one process is already we have discussed, which is called slip, okay. This is another deformation mechanism where you can have a deformation in some material. Actually, these materials are those which have inefficient slip system, okay. So, if you remember when we were discussing slip system, we said FCC is a very efficient system for slipping, okay. It has 12 close peg planes and close peg direction, a combination of 12 slip system, okay, and all the 12 have close peg planes and close peg direction, okay, which is what we want. In case of BCC, actually you do not have any plane which is a close peg plane. So, only some planes which are very near to that definition, okay, but again those are not very efficient. So, number of slip systems are very high, but none of them actually satisfy the close peg condition. So, actually you do not get very high ductility in BCC as compared to an FCC crystal. HCP, again you have some planes which are close peg planes and close peg direction, but the number is very small, only you have 3 slip systems like that, okay, in the basal plane 0001 plane. Okay, so, this is a very important process. The twinning process is very important process in this kind of system, where they do not have efficient slip system. So, for example, in hexagonal material like zinc, magnesium, at room temperature, if you do any deformation, you will always going to get some twinning. In BCC material also, for example, steel at subambient temperature, it will deform by a slipping process, okay. At a little bit high temperature, okay, the deformation by slip process becomes easier, okay, because at high temperature it becomes easier for you to slide the atom over one another. So, there you will not see the deformation through twinning, but if you go to low temperature, okay, then you will start seeing that the deformation is through twinning process, okay. Now, why actually this twinning takes place? Okay, just a comparison. Okay, in this case we are deforming a single crystal. Okay, and you can see that the slip is taking place on some crystallographic planes where you have satisfied the maximum Schmidt factor condition. Okay, so the crystals are sliding over one another. Now, the problem is, let us take an example of HCP crystal. We know that the efficient slip system or the closed spec condition which we have is satisfied by this slip system. What if this particular slip system is not oriented such that it is going to give you the maximum Schmidt factor? Okay, you are applying stress, okay, you are deforming the single crystal. Okay, now my stress is continuously increasing in the system. Okay, but if my this basal plane is not oriented such that you are able to reach the maximum Schmidt factor, okay, or maximum resolved stress, resolved shear stress, okay, then how it is going to deform? Okay, you can keep on putting the stress in the system. So, what material will try to do is it will try to reorient the crystal, okay, and we already know that twinning actually reorients the crystal, okay, you get a mirror image, so reorientation takes place. So, I can reorient the crystal. So, the initial arrangement is not able to give me the maximum resolved shear stress for slipping process. So, what my material is trying to do is now it has reoriented the crystal here. Okay, you can see now the orientation or the arrangement has changed. Okay, and by doing that, the material is trying to align now these planes such that they will be able to deform plastically. Okay, deform by a slip process. Okay, so this is the whole idea of bringing twin into the system, that to reorient the crystal such that you are able to satisfy the condition for deformation in some slip planes where you have closed spec arrangement. Okay. So, this is about the deformation twinning, and with that our deformation kind of how the plastic deformation mechanism is there. Okay, so one is slip, another is twinning will be completed. Okay, now we will use these ideas about deformation through dislocation and all these things to understand that can I do something to my material so that the strength of the material can be enhanced. Okay. So, that is what now is our concern, that if I can do something to the material, okay, and that is why where the whole engineering comes, the whole design, the material design comes, that how I can change the microstructure, or I can change the or tailor the microstructure to get the properties which I desire. Okay, so can I manipulate this to get strengthening in the material, because strength is one of the important parameter to understand and to get in the material. So, that is what we will start with in the next lecture. Okay, so thank you.